Hey there, Calc 3 folks, back here with another video in our study of vector calculus. Just a few more to go until we are at the end here, where we are going to, in the next couple of videos, introduce you to surface integrals, right? And a surface integral is analogous to the case of a linear integral, where back when we were introducing the linear integral, we considered our curve over which we were integrating to be defined parametrically. Well, we are going to see an analogous technique here in the case of a surface integral, right? Where what we need to do in order to introduce the idea of a surface integral is introduce, first of all, the concept of a parametric surface. So that is what my video begins with here, is introducing you to parametric surfaces. And one of the ways we introduce them is we go back and we just take note on what it meant to be a parametric curve, right? We are familiar with defining a curve in R sub n using the parametric description of a curve given by a vector valued function r bar of t for the parameter of t, where in two-dimensional space we saw a depiction of r bar of t given by the vector x of t comma y of t, where x and y were the values of position in the xy coordinate plane dependent upon the values of t, the parameter t. And in r sub 3 we added on a component z of t to describe position with respect to the value z in three-dimensional space dependent upon that parameter t. All right? Where, to begin with, recall what we had for a parametric curve. We had these descriptions given by our vector valued functions, right? This description in R2 and this description in R3. All right? Now, in the case of a parametric surface in n-dimensional space, right, the vector valued function r bar is still going to be used, but it's going to be defined in terms of just now, well, in terms of now, the case for having two parameters, where instead of using t, we might consider using the parameters u and v, where our surface can be defined parametrically by the vector valued function, or which we will note here is now actually a multivariable vector valued function, r bar of u comma v. Right? That describes our surface, right, in terms of the parameters u and v, right, in terms of these parameters that describe some behavior in two-dimensional space, right? A parametric surface is described by a multivariable vector valued function. A parametric curve is described by a single value, a single parameter vector valued function, whereas here we're going to see a multivariable vector valued function, a case with multi-parameters, right? Multivariable, what we might actually say is a be a little bit more specific, a multi-parameter vector valued function, right? U and v playing the role of the parameters in this function. If we were to get into the specifics and dimensions of space, right, in two-dimensional space, a parametric surface would be described by r bar of u, where x and y would be defined as multivariable functions of u and v, parameters u and v, right? Whereas in three-dimensional space, we would see a parametric surface described by r bar of u comma v equal to the three-dimensional vector, where the components x, y, and z are themselves multivariable functions of the parameters u and v, right? A description of a surface that is rather analogous to our descriptions of a curve seen in two- and three-dimensional space defined parametrically, where instead of just working with one parameter, we're now going to define it in terms of two, the parameters u and the parameters v. All right? We might consider an example here. I do think I delve into an example. Yeah. Consider the parametric surface here, defined by r bar u comma v. Here, this surface is going to exist in 3 dimensions, an x dimension, a y dimension, and a z dimension, where in the x dimension we are a multivariable function of u and v that is just strictly dependent upon u. It's u. Y is a multivariable function of u and v, which, however, is strictly dependent upon v. And z is a multivariable function of parameters u and v that actually depends upon both u and v, where z is equal to u squared plus v squared. And this is over values of u and v, the parameters, let's say, where we might say that this is over a region R in 2 dimensions, where u is between the values of 0, 1, and v is between the values of 0 and 1. All right, defining what we might say is a square region in 2-dimensional space. All right, note R, as we have said, is a square region in 2-dimensional space, and the parametric surface is actually a portion of the paraboloid defined in R3 over region R, where our location for x and our location for y will be very similar to our locations for u and v, right? In fact, u is equal to x and v is equal to y. Where now z is equal to x squared plus, well, u squared plus v squared, where if x equals u and y equals v, z is going to be equal to the equation x squared plus y squared, which defines a paraboloid in its behavior, right? Which is only interested in being values of x and y, or what we would consider parameters u and v, over this square region. And if we consider the illustration, this would be the illustration of this parametric surface. It is this surface that forms where your location for x is going to be given by u, your location for y is going to be given by v, where u and v are just values both between 0 and 1, right? And the intersection of u between 0 and 1 with v between 0 and 1. Defining the square region in 2-dimensional space where the actual height of the surface is determined by u squared plus v squared, which defines this parabolic shape, right? I should really say paraboloid shape over this region R in 3 dimensions. This portion of this paraboloid becomes our parametric surface defined over this region of R. All right. Now, let me get this right. Now, that's parametric surfaces, folks. That's an introduction to parametric surfaces. It's essentially a multivariable vector valued function, defines a parametric surface over values of the parameter defined in 2-dimensional space as region R here. All right? Very analogous to how we define a parametric curve in n-dimensional space, or as we have seen in 2 dimensions and 3 dimensions, where a 2 or 3-dimensional description of a curve can be defined in terms of just one value of a parameter t, using these vector valued functions that are solely based upon a single parameter value. Right? So, now that we've introduced surface integrals, we can start to consider the case of a surface integral applied to a function. Now, we have considered applying this, the surface integral operator before, when we've considered applying the double integral operator on a scalar valued function, right? We understand that when we apply a double integral operator on a scalar valued function, right, this calculation, right, is going to be considered a surface integral that yields either net volume or what we call hypernet volume over this surface we define as region R. Right? It is a special case, right, of a surface integral, right? What we note here, it is a unique case of a more generic calculation known as a surface integral, where the case of the double integral over R for function f, right, all integrated with respect to the area of R, right? R, region R, we might say here, region R defines a surface contained in two-dimensional space. It is the unique case where our surface is laid out flat in its two-dimensional space, right? But what we can take note on, and this was true with the case of lines, lines are what we might think of as a one-dimensional object, but they can be warped and twisted and curled in n-dimensional space. And the same can be said about a surface. A surface exists naturally in a two-dimensional space, as what we might say is a flat surface. But that flat surface itself can be warped into three and furthermore into n-dimensional space. That surface, that two-dimensional description of a region, doesn't have to just exist in two dimensions. It can exist as a two-dimensional description of a region in n-dimensional space. And we can integrate over that two-dimensional description of a region in n-dimensional space using what is known as a surface integral. And much like with the linear integral calculation, there is going to be some transformation that occurs in the calculation, right, when we consider the warping of the space into some nth dimension. All right. The formal definition here we see is given as follows. If we assume f defines a scalar valued function in three-dimensional space over a surface S defined parametrically as r bar of u comma v equal to the multivariable vector valued function x of u v, y of u v, z of u v for the components, where the components are multivariable functions, multivariable or multi-parameter functions of parameters u and v that describe a region of R in two-dimensional space where u is between a and b and v might be between the bounds of c and d. All right. Let's assume that we have this three-dimensional function, right, that is occurring over this smooth surface S defined parametrically here, given in three-dimensional space. Right? The surface integral of f over S with respect to the surface area parameter, which we also denote is capital S, is given by this calculation seen here. And it's given in general by this argument, right? This is illustrating the surface integral over surface S, where we have an integration with respect to the surface area of S. Both the surface and the surface area are illustrated using or denoted using a capital S in this notation, where this surface integral operator is being applied to some scalar valued function little f. And when this is applied to the scalar valued function little f, this can be translated into what would be considered a double integral operation that occurs over this regional description given by R and happens with respect to the area of R. And this is done by transforming that scalar valued function f, right, as the integrand in this surface integral operation highlighted here into this integral seen here, where this integral, right, is the product here. What we might notice is going to be a product of function, the scalar valued function f, expressed in terms of these parameters u and v. And the way we're going to express f in terms of the parameters u and v is very similar to how we took a description of f and made this transformation for a parameter t, we're going to take these descriptions of x, y, and z in terms of u and v, substitute them into f for x, y, and z, and obtain a description of f in terms of parameters u and v. And that's going to be multiplied by this scalar factor. Now, what the scalar factor is a description of, we call that Jacobian multiplier. In fact, this is what describes the process of finding that Jacobian multiplier back in our study of the Jacobian, right? It is multiplied by the magnitude of these two vectors, t bar of u crossed with t bar of v. T bar sub u crossed with t bar of v's magnitude is going to be what we call that Jacobian multiplier when transforming this surface integral in terms of surface S and the what we would call surface area parameter into this double integral calculation over a two-dimensional region R in two-dimensional space defined with respect to just the area of R in two dimensions. All right? Now, we do go a little further. What are these two vectors used in the cross product? Well, they are, right? They are defined as, right, the partials of our parametric description for the surface, right? R bar of u comma v with respect to u, right, for the case of t bar of sub u, right, which is just going through R bar of u and looking at the partials of the x, y, and z component with respect to u. And t bar of v, right, is the partial of R bar of u, our parametric description of surface S over region R, right, with respect to the parameter v, where it is the partial of x with respect to v, the partial of y with respect to v, and the partial of z with respect to v. If I take these two vectors formed by the partial, take their cross product, sorry about that, folks. So if we take the cross product, right, of those two vectors, those two what we would call vectors formed by these partials of R bar of u in terms of u and in terms of v, if we cross them, we will get a vector description, where if we take the magnitude of that vector description, that magnitude is going to be scalar in value and be the scalar multiple of what would be function f in terms of u and v, right? Forming the integrand of our double integral calculation over region R, right? This magnitude of this cross product, again, being that Jacobian multiplier in the transformation of surface S into surface R in its description, right? And this calculation does begin with determining these vectors and determining the scalar multiple. Now, one thing we do note, in general, the surface integral operator itself applied to just what we might consider to be an integrand of 1, right, is going to be equivalent to just this calculation itself in the context of region R, right, in two-dimensional space for parameters u and v, right, which defines in itself what we would call the surface area of S. If we find the surface integral over surface S with respect to the surface area of S for just the argument of 1, that will just give us the surface area of S, which in terms of how we're going to calculate that is we are going to interpret it as this double integral in the context of R, where S has been defined parametrically, right, as seen above. Now, we might consider a case here. We might consider the case for calculating the surface area for the surface S, right, where S here is being defined parametrically as this set of, this multivariable vector valued function, right, where the x behavior is described by 3 times parameter u, the y behavior is described by 5 times parameter v, and the z behavior for the surface is described by 1 minus 2 times u minus 2 times v. And what this parametric surface describes in this context over values of u and v in this region R, where u is, where region R defines a two-dimensional region of space, where u is between 0 and 1 and v is between 0 and 1, is what we call a planar surface. Where in this particular case, we would have that planar surface illustrated as we see here, right? It is this plane, this region of the plane in three-dimensional space that is forming, we say, over this region of R that would exist in 2 dimensions. That would exist in the plane where z equals 0 for values of u between 0 and 1 and values of v between 0 and 1, which would correspond to, in terms of x, because of the relationship here, if u is between values of 0 and 1, x will be then between values of 0 and 3, which we see is the description of x for this region of R, illustrated here. And if v is a value between 0 and 1, it's going to translate to a region in terms of x that's between, what, 0 and 5 in value, which is what we see here for this measurement on R. As for s, it's going to be then determined by 1 minus 2u minus 2v, which gives us the height of the surface S in this three-dimensional space, which gives us this measurement for z measured along these axes, right? If I'm at u of 1 and I'm at v of 1, I will be at a height of z minus 2, or a height of negative 3. That would put me at this height, at this very corner of the parametric surface, all right? And if I wanted to calculate the area of that surface, right, we would note that the partial of our parametric description for that surface in terms of u would just be 3, 0, negative 2, and notice that is just going through this description of u, or sorry, this description of s and taking the partial of this with respect to u. Here that would be 3 for the first component, 0 for the second, and negative 2 for the third. That's going to be t bar of little u, sub u. And if I do that with respect to v, that's now going to be 0, 5, negative 2. And you can see those are the vector descriptions I get down below here for t bar of u and t bar of v. Where what am I going to want to do with these two vectors in my calculation? Here, if we're considering surface area, I'm going to want to find the magnitude of their cross products. I'm going to need the cross product of those two vectors and then the magnitude of that. Where, if we think about the cross product, it is this determinant calculation, which would result in the vector 10, 6, 15, where if I take the magnitude of the vector 10, 6, 15, I will get the square root of 361, which is equivalent to 19 in value. All right? And 19 will become the scalar multiple I incorporate into the integrand here for the double integral over what's now going to be region R, where region R is simply this region of space where u and v are between 0 and 1 in value. All right? So if I set that up down here to give me the surface area, right, for that planar surface, that double integral over that surface with respect to the surface when the integrand is simply 1. All right. Oh, let me get that in the right location. All right. Is equal to, like we said, just the double integral over region R, which is defined as being values of u between 0 and 1 and values of v between 0 and 1 simultaneously, for an argument given by the scalar multiple of this, what, magnitude, right? The square root of 19, or sorry, the square root of 361 or 19 in value, which when you integrate it with respect to u is just 19u, and when evaluated from 0 to 1, that becomes again 19. Where when 19 again is evaluated across with respect to v, it's 19v, where across the bounds from 0 to 1, again, it becomes 19. So the area of that planar surface given above is 19 units squared. And that could likely be determined if you were just to calculate the measurements for these side lengths of this, the surface S in three-dimensional space. Right? If we take note of what would actually be the description of this rectangular region R over which S is defined, if that is 5 units by 3 units, that's 15 square units. Well, S is certainly, because of its tiltedness in the space there, its skewness in the space, is going to have an area greater than 15 units squared, and we found that it's 19 units squared, which does fit this picture, right? Which would be a good approximation at the very least, but it is exact, right? It fits the illustration of what we would have for the area of surface S in this picture. All right? Notice that is just a surface area calculation. We can take that further and actually consider calculating, right, a double integral, a surface integral for a scalar valued function f with respect to the surface area of S, where in this case we might consider having function f be the multivariable function just described by y, right? And S is defined as the surface in R3, right, where x squared plus y squared is equal to 1, and z is between the values of 0 and 2, right? What that is going to describe here for this surface is this lateral edge of this cylinder. This cylinder, whose cross-section in the xy plane is defined by the unit circle, a circle centered at the origin with a radius of 1, that extends, or we might say extrudes itself into the z-dimensional space, the third dimension, for values of z from 0 to 2. If we took that unit circle in the xy plane and extruded it through z, right, through the third dimension from 0 to 2, it would form the lateral edge of this cylinder. All right? And what we want is the surface integral, the integral across the lateral edge of this cylinder, right, for what is the scalar valued function f, right? The scalar valued function f, which is equal to the value of y, right? And the scalar value here, right, in the case of the surface S, right, can be expressed parametrically, right? This can be expressed parametrically as the surface R given by theta comma z. Where here I'm going to grab these descriptions of parameters given in the cylindrical coordinate space, right? Where if I consider the surface R bar, or S, being defined parametrically in terms of the cylindrical coordinate space, I could use parameter theta and parameter z to describe this surface, where my x location is going to be given by the cosine of theta, my y location might be considered to be given by the sine of theta, and my z location just given by the location of z itself. Where here, for theta and z, theta is considered to be happening between 0 and 2 pi, which is going to account for all the points around the unit circle, and z is going to account for values from 0 to 2, which is going to be the height of the cylinder. All right? And if we calculate that surface integral, Right? That does start by considering what is going to be the partial of our parameterization of the surface with respect to the parameter theta. What's going to be that partial vector, right? And what's going to be the partial vector with respect to z for r bar of theta comma z. And if we apply our partial operator across this with respect to theta and z, we will produce, for the case of theta, negative sine theta cosine theta 0. And for the case of z, the vector 0, 0, 1. Where if I arrange those into a cross product operation, right, we will see that the cross product will result in cosine theta sine theta comma 0, right? Cosine theta 1, cosine of theta times 1 minus 0 times 0 is the cosine of theta. The opposite of negative sine theta times 1 minus 0 times 0 is the sine theta. And the cross product of the negative sine was 0 minus the cosine was 0 is itself 0. So this would be our cross product operation, our calculation for the two vectors found above. And the magnitude of that would be just given by the square root of the cosine squared theta plus the sine squared theta, which the cosine squared theta, sine squared theta is equivalent to 1 in value using our Pythagorean identity. So what we have here is the square root of 1, which is itself just equivalent to 1. Right? So in the surface integral of our surface f in this case, where f is this function of just y, right? Since r of theta comma z equals cosine theta sine theta z, where y is equal to sine of theta, f in terms of those parameters theta and z would simply be the sine of theta. And the surface integral of f over surface s would be defined as follows. It would be this, right? This, in general, this surface integral applied to f in general with respect to s, we're defined, if s is defined parametrically as seen above, we can translate that surface integral calculation into this scene here, where f defined in terms of the parameters theta and z would just be the sine of theta, times by this magnitude, which given down below here is going to be the magnitude of 1, right? Which we might do here is, let's say this is, let's go ahead and rewrite this as f of theta comma z, right? Which is going to be the sine of theta times this magnitude of this cross product, which we calculated to be 1. So that's just going to be times by 1. And what we end up building is this double integral here over region R, where region R was defined by values of theta between 0 and 2 pi, and values of z between 0 and 2, applied to just the sine of theta. And integrated first with respect to z would be just sine of theta times z. From 0 to 2, evaluated from 0 to 2 would result in this 2 sine theta. Where if 2 sine theta now is integrated with respect to theta from 0 to 2 pi, you will get negative 2 cosine theta, where when evaluated from 0 to 2 pi produces negative 2 minus negative 2 in value, which simplifies to the value of 0 in the end. And what we end up calculating here, folks, right, is the surface integral of f over surface s, where this number is 0 in the end, that you go, well, what does that all mean in terms of value here? If we go back to our picture, what's lacking in this picture is surface f moving through this space. But if you think about f being just the value of y, it does not depend upon x, it does not depend upon z, right? Function f solely depends upon what is our value of y. And as y goes from negative infinity to positive infinity, what this is going to be is a plane crossing through this space, right? Where what we are finding is the amount of space trapped between this plane moving through space, where that plane solely depends upon the value of y, right? And this surface S, where due to the symmetry, this net volume of space is canceling. Some of that space is occurring over function f, some of that space is occurring under function f, where the amount of space trapped above and below this, what would technically be a net volume of space, would be balanced and would zero out, right, in its description. Again, keep in mind what we are calculating with a double integral is a net volume or a hypernet volume description. So when we calculate this calculation of 0 down here below, if we were to give it some units of measurement, we might say this is 0 units cubed, because it is describing what we might say is a volume of space. And this net volume of space being described here in this situation is 0 in its value, in its spatial description. All right? And folks, that is, again, just surface integrals of vector valued functions, or not vector valued, of scalar valued functions, where we've seen these before, right? We're just now applying these concepts over a surface that doesn't necessarily just exist in 2 dimensions, but is allowed to curve in 3-dimensional space over some 2-dimensional region defined by R. All right? But with that said, I have another video here looking at surface integrals over vector fields, right? Where we're actually going to see the surface integral calculation come into play to help us calculate, what would we say, is the case for outward flux across a 3-dimensional surface, and, well, or flux across, outward flux across a 3-dimensional surface, and what would be considered, well, it's going to come about also in what we're going to see as Stokes' theorem, right? These surface integral calculations. And this is leading us to really an analogous, well, this is an analogous idea to the linear integral, and is leading us to an analogous idea for what would be considered the integration over a solid, or what would be called a solid integral, a triple integral that occurs in 3-dimensional space, right? So folks, with that said, I will stop the lecture there. I hope you're doing well, and I'll see you all next time.